Now, I'd like to talk today about quantum machines. You've heard, I'm sure, that certain kinds of quantum machines are impossible. And what I'm going to do is show you, in a sense, how to get around that. But what I'm really going to do is change the rules a little bit, loosen them, so that the impossibility proofs go away. The first one that you've heard about, I'm sure, is no cloning. So that's going to be one of the things that we're going to be taking a look at. Another one, which is less well known, is what's called a universal NOT gate. So U NOT. So what does that do? So suppose I have a qubit in state alpha 0. And I want to produce a state that is perpendicular to it. So what I want to do is this. So I would like to build some kind of a device that takes me from this state to this state. Now, that's also impossible. Why? Well, here the proof is very simple. The fact that you're getting complex conjugates here means that the operator is not unitary, but is anti-unitary. Quantum mechanics only has unitary transformations, so it really cannot do something like this. So this is the second impossible thing. We can't clone, and we can't make a universal spin flip, or the so-called universal NOT gate that simply takes something to something that's perpendicular. So since we can't do these things, why am I telling you about them? Well, we're going to discuss two strategies for dealing with this. We're going to be paying attention to mainly one of those strategies, but let me just mention both. The two strategies are the following. You can do the operation you can do it probabilistically, or you can do it approximately. What do I mean by those two things? Probabilistically means that I can build a device and it's going to do something, and then I'm going to measure it. And the measurement can give me one of two results. It can either tell me that it did what I wanted it to do, or it can tell me that it didn't do what I wanted it to do. So with a certain probability, it will do one of these impossible operations, but on the other times, it's simply going to fail to do it. Approximately means that the output states of the device are going to look approximately like what I want, but not exactly. So the no cloning theorem is actually better stated as it is impossible to create perfect clones of an arbitrary quantum state. You can produce approximate clones of quantum states, and that's what we're going to discuss. So just as an example, let me discuss probabilistic cloning. Okay, I'm not going to spend very much time on this, and it's going to be a rather sketchy discussion. We're going to pay far more attention to the approximate cloning. So probabilistic cloning does the following thing. So I have a machine, and I'm going to put a qubit into it, and that qubit is going to be in state psi j. And there are two possibilities. Okay, so I'm only going to allow two possible inputs, and I don't know which one I'm going to put in, and then what comes out are two copies psi j. And the machine also has a light on top of it. And the light tells me whether the operation succeeded or failed. So I put my qubit into the machine, and if the light goes off, then this is exactly what's happened. I produced 2 copies of the input Q bit. So let me just indicate like this with the light on, and that means that the procedure has succeeded. The other thing that can happen is that you put the Q bit in and the light doesn't go off. And that means the procedure failed. So those are the 2 possibilities. So this is a probabilistic cloner. Sometimes it works and sometimes it doesn't, but it tells you which of the 2 things it did. If the light goes on, it tells you it worked. If the light doesn't go on, it tells you that it didn't work. And the probability that it works depends on the states that you put into the system. Okay, now I'd like to move on to the approximate cloning.